Hello everyone. We are going to listen now spispy open source SPI flash emulation by Trammell.
So I'm really glad that everyone is here today to learn about the spispy flash emulator. This project I've been working on for the past few months, and it's a open source tool that lets us more quickly work with SPI flashes. And hopefully, at the end of the talk, you'll understand what those are, why we're doing it, and how it works. So first, let's talk about what is a SPI flash. And if we look at a motherboard, there are some small chips on it that store the firmware that the CPU executes before it loads the operating system. And in days past, these were around 64 kilobytes, and they stored the BIOS. These days, there's a lot more complexity. Typically, things like the closed source UEFI firmware, but there's also open source firmware like Linux boot and Core boot that you can install into those flashes. If we get really close to the flash, we can make out the part number, and we can look up that data sheet to find out some more about it. This gives us the definition of SPI as serial peripheral interface, which is a pretty generic term. In this case, they're typically three or four wires. It also tells us that the size of it is 128 megabits. This one's 16 megabytes, which may not seem like a lot in this modern era of gigabyte or terabyte SD cards, but it's a huge step up from the 64K we used to have. So why do we want to emulate SPI flashes? Well, if you're working on open source firmware like Core boot or Linux boot, or if you're doing security research on the closed source things like UEFI, you end up having to reflash these chips a lot. In fact, I have spent an enormous amount of my time in the past few years reflashing these chips, and it is really, really slow. And you might think, it's only 16 megabytes. How slow could it be? And the problem is that these are designed to be ROMs. They're not designed to be updated all the time. So they haven't optimized for the write speed. You have to erase them 4 kilobytes at a time. And in the worst case, it's 120 milliseconds to erase a 4K sector. So if we do the math, 120 milliseconds times 16 megs divided by 4, we're talking about 8 minutes to rewrite one of these things. And that's an enormous amount of time to spend every time you want to reprogram it. So let's look at how this works out for a day in the life of a Core boot developer. You finally finished building Core boot, and it's time to flash it. But first, you have to turn off the power to the machine you're going to flash because the flashes aren't multi-mastered. You then have to carefully attach your flash programmer because most of the commercial flash programmers won't let you tri-state the lines, so you can't boot with them attached. And then you can finally run flash ROM to start flashing. The first bit goes pretty fast because you probably haven't changed the management engine section unless you're doing security research on that, which I used to do as well. And then it hits the Core boot part, and it has to start erasing those blocks. And yeah, 3 minutes in, it's still slowly erasing and writing. 5 minutes in, I mean, this is not the way you want to spend your day waiting for these chips. So finally, 5.5 minutes later at 49 kilobytes per second, we're talking about dial-up modem speeds. It's finally done flashing. But you're not done yet, because now you have to remove the flash programmer clip from the board, power on the machine, and hopefully it boots. But if you've done firmware development, it probably doesn't. And you have to rebuild and reflash, and this is how I used to spend my day. And like they say on TV, there's got to be a better way. So what I want to show you today is a live demo. So can I get a volunteer with a ThinkPad X220 or 230? Can't promise it's not going to get bricked, but thus far I have not bricked any. But if I do brick it, you can keep both pieces. So, yes, but I love it. Thank you, sir. What I love about hacker conferences is there's always somebody willing to jump up with that. So, I guess let's boot it and see what it comes up with. And this should just be the stock firmware. UEFI takes a little while sometimes. Okay, this is the stock firmware. So we're gonna power it off. And the nice thing about the X200s is the flash chip is very accessible underneath the mouse pad.
You've done this before.
All right, so here we have the SPI flash chip, and we have the SPI. So we're going to attach it to it. Making sure to note pin 1 is the one with the dot on it. Okay, so I've built a core boot image, and now we're going to upload it with the spispy tool into the board and put it in monitor mode. So this is going at USB serial speeds, about 1 megabyte per second. Okay, it's now in monitor mode, so when we turn on the machine, we get a printout from a bunch of things, and now we have CBIOS from the core boot tree up and running. So this is way faster than 8 minutes. But wait, there's more. So, as I mentioned, you frequently end up having to change these things all the time. And when you're doing firmware development, you end up having to tweak them. So we're gonna modify the firmware. And we're going to rebuild core boot and CBIOS. Okay, and now we're going to upload just the core boot section. That's pretty fast. And now when we boot it, we're going to get something a little different. All right. So this is a way, if you're doing this sort of firmware development, this is a way to make it way, way faster and way more convenient. It also lets us start to think about adding other things like fuzzing and continuous integration into our firmware development trees. So, okay, that's enough for the demo. All right, so we can skip the parts about, if it didn't work with the demo. So that loaded at 1 megabyte per second, which was limited by the USB serial port that we've implemented in the FPGA. We can definitely get a lot faster than that, but this is just worlds better, so haven't been motivated to really go into it that much yet. The other big difference is we can now soft reboot into these new firmwares. We don't necessarily have to power cycle. We don't have to keep removing the flash programmer. So that also speeds up the time. The other really neat thing that this gives us is insight into what the CPU is doing when it starts up. If you've just come here to Congress from the 1970s, you might think that the x86 loads the legacy reset vector from the top of memory and jumps into it. But that is no longer what actually happens. So if you watched my computer screen when the system was booting, it printed out a bunch of read addresses. And we can correlate those with what's in the ROM contents to see what the CPU is doing as it starts up. The first thing that happens is it loads the platform controller hub, reads the Intel flash descriptor to determine what type of chip there is. Then the Intel management engine reads its firmware and gets running. The ME starts the x86, but it doesn't go to the reset vector. Instead, CPU microcode finds the firmware interface table, parses it, and then looks for microcode updates and applies them to the CPU. If you have a boot guard equipped CPU, which this one is not, the boot guard ACM is then fetched, validated, and run. And then finally, we get to the reset vector, which jumps into the BIOS. In this case, 13,000 reads from the flash chip later. So yeah, the way systems have started up has completely changed, but we can now see that by watching this. It's kind of like Wireshark for the SPI bus. If we plot those addresses versus time, we also can find some interesting patterns. So there's addresses on the y-axis, time on the x-axis, and I've colored the addresses based on if they're the first time the address is read or the second time. So this linear scan of those addresses is when bootguard is doing a signature check on part of the firmware, which means these rereads of those addresses are a time check, time of use security vulnerability potentially. And my colleague Peter Bosch and I were able to leverage that to get a root of trust bypass in Intel's bootguard that they are still working on mitigating. We went through disclosure with them about 150 days, and finally they said it's taking too long for them, and we were cleared to go ahead and present it at Hack in the Box in Amsterdam a few months ago. So, again, this is a computer congress, and you all are very technical. So let's talk about how this works. And before we get into to the code, I really want to thank the projects that this project depends on. That with a lot of these open source projects, we're not developing it in isolation. We're building on the work that other people are doing that's really valuable. In this case, we're using the open source FPGA toolchain of Yosis, Project Trellis, and NextPNR that has completely revolutionized how FPGA development is being done. And I'm really excited that there's now a completely open source way to work with this sort of programmable hardware. I also want to thank the folks at RevSpace, the hackerspace in Den Haag, for letting me hang out there and work with some of them while we were developing these tools, specifically Alyssa Milburn and Peter Bosch. What we developed at RevSpace for the Hack in the Box demo was based on a small ICE40 FPGA. It has 1 megabit of block RAM, which isn't enough to store the whole firmware image, but it was enough to do our proof of concept for the time of check, time of use. In order to store the full one, we need something bigger. And again, hackerspaces came through and delivered a wonderful open source FPGA board. This is from a Croatian hackerspace that has a ECP5 FPGA and 32 megabytes of DRAM that we can read and write from at about 250 megabytes per second. SDRAM, or DRAM in general, is a really complex sort of design. It has all of these sort of dark magic state transitions that you have to deal with in order to be able to interface with it. And you know, I'm lazy. I don't want to have to implement that. But again, there's a wonderful open source tool that people have put out there. Stefan Christensen wrote and published a modular SDRAM bit of Verilog that we were able to we were able to merge into spispy and get working on the ECP5. I also want to give thanks to Scanlime, who, as with many projects, had already done something very similar. Back in 2009, she was emulating a Nintendo DS save cartridge, which is a very small SPI flash that's read at a very slow speed. But she documented enough of the protocol that it made it very easy for us to build on her work to build our emulator. So let's talk about what that protocol looks like. I mentioned that it's important to notice where the dot is on the chip, because in the data sheet that tells us which one is going to be pin 1. And I mentioned it's a 4-wire protocol. Obviously, power and ground is very important, but the chip select line is the one that tells the flash chip when it's time that it's the x86 wants to talk to it. And while that's low, the chip is selected. So we would say this is a active low signal, and we designate that with either an exclamation mark or a pound sign in the name. The next pin we need is the clock, which is moving at some speed controlled by the x86, and the data lines are clocked on the rising edge. They're sorted into the registers, so we would call this rising edge clocked. And then the serial inline is from the x86, and the protocol typically consists of a command byte followed by some number of address bytes. And then the SPI flash responds on the serial outline with some number of data bytes as well. And again, those are also rising edge clocked. If we go into the data sheet, we can see the read command, which is what the bulk of what we saw scrolling by were. And these have a 3-byte address into the flash. 3 bytes gives you 2 to the 24th, or 16 megabytes. Okay. And on the wire, we typically see the 03 followed by the 24 bits, followed by then up to 256 bytes of response data that get clocked out. And the Verilog code that we used for the Hack in the Box demo looked sort of like this. This is a little bit abbreviated, but basically on every rising edge of the SPI clock, we shift an address bit in from the data in line. We increment the number of bits we've received, and if we've received 23 bits, then we look up in our block RAM for the data at that address, and we shifted out the data out register. This worked wonderfully on the ICE40 with 1 megabit of block RAM. We were able to do our very small proof of concept, but when we tried doing this with the DRAM, it didn't work. What we ended up seeing is that the first bit coming out from that DRAM, when we clocked it out on the data outline, was delayed by about 50 nanoseconds from the rising edge of the clock. And that meant that we didn't meet timing, and the system just wouldn't even start up. It wouldn't boot because the data were almost always corrupted. And the reason for that is due to the way reads happen in DRAM. That what we think of as an atomic operation, where we say, index some address into the RAM, happens over multiple clock cycles, where on the first clock cycle, the row is addressed. And this is typically 12 bits out of it. Then some number of clock cycles later, a column from that row is addressed. And this has to do with the way DRAM is implemented. It has to copy values from a bunch of capacitors into registers, and then you can read from those registers. And this latency is typically 5 to 7 DRAM clocks, or 50 to 100 nanoseconds. And what's really interesting is this doesn't depend on the speed of the DRAM. That if you go to your brand new PC with 2.4 gigahertz DDR4, it probably takes about 100 nanoseconds to do a random read. It's just that caches do a good job of hiding that. But in this case, we don't know what what the read performance is going to be. So this is not going to work for us. And the problem that we're running into is that we don't control the clock. It's being controlled by the x86 that's talking to the flash emulator. So we basically have from the rising edge of that 24th bit to the falling edge of the clock to get some data available, which at a 20 megahertz SPI clock means we have to have a result in about 25 nanoseconds or less. Luckily, we have an open source memory controller that we're using, so we can modify it to let us do these sorts of things. In this case, what we do is we can detect, once we've received 14 bits of the address, we can actually go ahead and kick off the row activation. Once we received another 9 bits of the address, we can do the column read from that row. And then we get back 16 bits from that column, which means that on the falling edge, we can select either the upper or lower byte from that result and write it out to the data outline. And this actually worked. We're only about 10 nanoseconds slower than the real flash chip, which is enough to meet the timing, the setup and hold timing requirements for this for the read. And at a 20 megahertz clock. So we do actually have to cheat a little bit and not let the x86 run that clock faster. But luckily, that's a configuration in that flash descriptor. I think one of the things I'm most proud about with this project is that White Quark called it impressive. And she is an incredibly gifted hardware engineer, and for her to say that made me very, very proud. So if we go back and look at that waveform, we can actually read the data stream that's going, and the 010110 works out to be 5A5. If we look at the hex in the hex dump of the ROM, we can see that appears there on the in the Intel Flash descriptor. And based on what Butterworth and Kova documented in their advanced BIOS training, this is the valid flash descriptor. The CPU won't start up if that read doesn't come in. So getting that one to work was the first sort of key victory in getting the SPI to function. Unfortunately, it wasn't reliable. That a lot of times we could get most of the way into the firmware, but we'd frequently get sort of bad errors or CRC errors or decompression errors on the firmware. And this has to do with another quirk of DRAM, which is that there's a auto refresh cycle that every 7.8 microseconds you need to do a refresh command, which will choose a row from the RAM, copy it from capacitors to registers, and then copy it back to the capacitors. And this has to do with the fact that DRAM capacitors are slowly losing charge, so you have to continuously reread them and refresh them. Luckily, we have an open source DRAM controller, so we were able to add to the interface to it an additional input line that says hold off on doing a refresh. We're going to need the memory very, very soon. So when we get a read command, we can assert this wire into the DRAM controller, and it guarantees that we won't have any refresh cycles while the x86 is trying to read from us. So you might have noticed that we were using a solderless flash or chip clip when we put it on the board. And you might be thinking, but why doesn't the real flash chip respond? How do we override it? And it turns out that on most of these main boards, the SPI flash pins are connected via small series resistors to the PCH or the x86. So as long as we can sink more current than the PCH, we can change the value of this line. And because there's that resistor, it doesn't cause any damage to anything. So schematically, this is what the SPI looks like. When the PCH, the x86, asserts the chip select line, both the SPI flash and the FPGA pick that up. The SPI flash starts asserting data on the serial outline, but the FPGA drives the CS line high, which then causes the real SPI flash to turn off its output driver, essentially releasing the bus. And then the FPGA is able to send data on the bus without worrying about damaging the output drivers. The drawback is we can't tell when the PCH has stopped asserting the CS line. So we instead have a little bit of a hack that we watch the clock line. And once we haven't seen a clock toggle for some number of nanoseconds, we assume the PCH is no longer engaged in a transaction, and we can then unassert the CS and let the bus go back into the state where the platform controller hub can turn it on and off. So we have this working on laptops, as you saw. We also have it working on quite a few different server platforms that we've worked on. And if we zoom way into that first server mainboard that I put up, you'll see that there are actually two flash chips, one for the x86 and then one for the board management controller, which is, in this case, an ARM CPU that and most of the time runs Linux. We now have, as of last week, support for doing the same trick to override the chip select line on the A-Speed 2400 series and 2500 series ARM CPUs, which means we can use the SPI not only for core boot, Linux boot, and UEFI research, but also for things like OpenBMC and microBMC to help accelerate the firmware development there. And that works on this particular Supermicro board, which is also supported by core boot. So if you want a fully open server, this is one to check out. You might notice that everything I've talked about has been somewhat Intel specific. We are working with a group in Berlin on supporting the AMD CPUs. We have support for booting the PSP, which is Intel's version of the management engine off of spispy. And this is going to enable some interesting security research there, because much like the management engine, the PSP is a hardware root of trust that potentially can be key to a lot of security issues. It is open source, so we would love for you all to help out. There are quite a few things that we don't support right now. But if you have a system that needs dual or quad SPI or fast read, or if you want to help us with the user interface, or maybe support other buses like the LPC bus or eSPI, we'd love to be able to turn this into a Swiss Army knife of bus, man in the middle, and Toctal sort of projects. So you can check it out from GitHub. You can join us on the open source firmware Slack. I'm also love to take questions via Mastodon or Twitter. And with that, I'd like to open the floor up to any questions. And also to reassemble the victim laptop.
Hi. So first of all, congrats. These are really a couple of really great hacks. And so my question is, does this then open a door for running core boot on laptops newer than 230? Because if I understood correctly from your slide with the first time and second time of reading the memory, we could just the first time that it reads, we could just give him the original firmware, and the next time we could just run the core boot.
Yes. So the question is, can the spispy or something similar be used to enable core boot on bootguard equipped laptops? And yes, you can use this on most. I've successfully done so on a variety of ThinkPads. The X1 Gen 6 was the one that I was using in that particular attack. It would require a hardware implant because bypassing bootguard is a per boot sort of thing. But using, I built a small mock-up with the ICE40 UP5K that would actually fit underneath a SPI flash chip, and you could then solder on top. it's somewhat inspired by my BMC hardware implant talk that I gave at Congress last year. The other option, however, is if the 9 Elements folks have a core boot port for the the T480S, which is a brand new boot guard equipped one that they've been able to get without boot guard enabled, direct from Lenovo.
No, just a small question. The ThinkPad that you flashed basically to a new bootstrap, are you going to flash it back? Or is it going to flash it back itself?
There were no changes made to the ThinkPad. Once the clip is removed, it is back to the, it will boot from the usual flash. So it's useful both for firmware development and evil mate attacks.
Okay.
Yeah, there it goes. Normal firmware.
Can you dump the BIOS and flash me the Balcon core boot edition, please?
I didn't actually verify that it boots. It did look like it got into Grub, but I'm not sure about if it goes the rest of the way. However,
And you can also flash with the tool the stuff on the chip, or only read out and override.
right now the Verilog only supports the emulation mode, but would be a useful feature to add, is something that would say read out the current contents of the chip to pre-populate the DRAM, let you tweak just a few pieces of it, test it, and then maybe write that back to the flash. That would be a good feature to add. Feel free to open a GitHub issue and assign it to yourself.
Thank you very much. If I have some free time left, we can speak about it.
Is there any sort of sensible mitigation that the manufacturers wanted to do to prevent the sort of evil maid attacks you were talking about?
So Intel Boot Guard, it does a really good job of preventing a lot of evil maid attacks, firmware level evil maid attacks, just because it does provide a root of trust in hardware chained from the management engine into the x86. So that largely has eliminated evil maid firmware attacks for systems that have it enabled. Other vendors are taking a different approach. For instance, Apple has the T2 security coprocessor that is doing a very similar thing to the spispy, where it is doing firmware validation prior to releasing the x86 from reset, and then delivering this validated firmware over eSPI to the x86. That's a really neat way to do it. Unfortunately, it's closed source. It's a proprietary solution that only works on their proprietary platform. Google has done a similar thing with the Chromebooks, that they have their Titan chip that replaces both sort of the embedded controller and the TPM and a few other functions. And it does a similar validation prior to releasing reset, at least in the server class ones. In the Chromebook ones, I think it only does validation at firmware load time. That they're not, evil maid physical attacks are not in the Chromebook security model. Microsoft Cerberus has also some similar things, but currently vaporware as far as actual chips for end users.
Any more questions?
All right. Well, I will be around all week, so if you have laptops and you want to try it out, love to test it on a variety of them. And again, feel free to connect on a variety of places, and love to chat further.